All right. Let's start. We are a little bit late, so if you want to be on time for lunch, please sit down. Come on, guys.
Oh, wow. 25 minutes late. You're going to be in trouble again.
Yeah, so we need to be on time for lunch. They're asked that we're on time.
Beautiful notes.
All right, so as I think a very good transition from what we've learned yesterday, we're moving to Waveforms 1 with Anna, whom you already know, who prepared us a nice presentation about perturbation models.
Okay. Yeah, so today or this morning, whatever you want to call this time of day, I'll be doing perturbation models, and then later after lunch in the late afternoon, Marta and Eleanor will be doing they'll be doing merger ring down. I heard someone saying they thought this might be quasi-normal modes. Quasi-normal modes is later for the merger ring down. Okay, so perturbation theory, what I'm going to be basically going over is I'll do a brief overview of post-Newtonian and kind of the concept of how it works. And then I will switch to self-force towards these beautiful systems, MREs. Okay, so let's get going. Part A, post-Newtonian theory. Okay, so I thought I'd start where I kind of left you guys yesterday. So the post-Newtonian theory, as you see, just to remind you all, remember we have our parameter space. This is as the binary is spiraling together. So then your merger ring then are here. This is our mass ratio when they're kind of the same size, and this is when one's a lot smaller than the other. Okay, and post-Newtonian, all mass ratios just breaks down as it speeds up because it is a perturbation in the speed of the system. Okay, so what I said yesterday was you do a perturbation from flat space-time. So we have Minkowskian space-time as our base, and then we do a metric perturbation. When we talk about post-Newtonian, it's with the speed of the system, which is why it breaks down as it gets to merger, because as you can imagine, as you're radiating that energy away and your orbit is shrinking, the black hole starts speeding up. And then they start moving at a considerable fraction of the speed of light, and therefore you have to break down. But it gets much closer than it's anticipated. There's also the post-Minkowskian gravitational potential perturbation, and that's when you perturb in your gravitational constant. The way I'm going to do it today, it's kind of combining these two, which is actually done a lot, but you can always stick to one or the other and then use to overlap. Okay. So one of the cool things about post-Newtonian and Minkowskians is these were initially implemented by Einstein when he was trying to figure out his field equations. So things like when he figured out does everyone know the story about the perihelion of Mercury? And that Mercury's orbit shifts, and it was off by what Newtonian physics said. And when Einstein came up with his whole theory, he calculated by doing a linear perturbation and realized his theory actually accounted for this extra shift that Newtonian couldn't. So immediately he had an observational proof that his theory could be the right one. He also used it to figure out that gravitational waves existed, although he made a mistake and thought they didn't exist, and then the journal corrected him and he got mad and then refused to ever publish with them again. And then someone decades and decades later, actually revealed who the reviewer was, because it was the first time he'd ever been reviewed. It was a new process. The whole concept was new. And it was one of the cosmology giants, so it was a person who knew what they were doing. And who then actually apparently sneakily told other people, like, tell them to go back and look at it. Anyway, so without this, we wouldn't have figured out our gravitational waves. Okay, also, more lately, it was used, I don't know if how much of the historical relativity talks you've been to over the years, but the first gravitational wave, the first Nobel Prize for gravitational wave physics, since there was one yesterday, wasn't the direct detection in the more recent years. It was actually in the 90s, And it was because of this binary pulsar that was observed, and they could see that the orbit was shrinking, and it seemed to be shrinking faster than it should. So a lot of post-Newtonian people did their post-Newtonian expansions, and they predicted it with general relativity. This would be the decay in the blue line, and the red dots were the observation points that were observed. So this was seen as an indirect detection of gravitational waves back in, like they started observing it in the 70s, but they continued with the observations. So that was one of the other great successes of post-Newtonian theory and the first gravitational wave Nobel Prize. Many more to come, yes. Okay, so next. Okay, so what I was going to do was kind of break down some of the stuff that Martha did yesterday and kind of show you how it's tied into the post-Newtonian. So one thing is the Landau lift shifts. So I don't know if everyone knows all those Landau lift shifts. Like they wrote a book on every part of theoretical physics you can imagine. But they also came up with this formalism for the harmonic coordinates and getting a nice wave equation. Okay, so there's going to be a little bit of math. This is all math. Okay, so you introduce a thing called the Gothic inverse metric. This looks gross. They even use a gross font. But it's just like the square root of your metric by your metric. Okay, so it's a tensor density. You're scaling it with the metric. Okay, and then you also have, and then I'm also just going to throw another definition and go, we're going to define another tensor density, which is this combination of this Gothic inverse metric. So just defining two things here, nothing crazy. Okay, then I'm going to show you an equation that I will not prove, because it's absolutely hell on earth to prove it, but it can be done. And it's basically that if you get two partial derivatives of this, you get out your Einstein tensor, and then with this very familiar factor, and then you get another tensor, which is, I'll show you now. Looks like this. I genuinely didn't want to latex this up. So it's disgusting, but you just take all the metrics, call it a T, Landau lift shifts, and now it looks pretty like this, and we'll never look at it again. Okay, so then the other thing you might notice is, okay, well, the Einstein tensor, I can just use my Einstein field equations and write that as my 8 pi GC over 4, the 8 hits the 2, I pull out my 16 pi g over C4, and now I have something that looks kind of nice. Cool. Okay, why did we introduce this tensor density? Well, one of the nice things about it has the same symmetries as the Riemann tensor. And any of you can check this. So you could just ignore this part for a sec. Even if you, okay, so our Riemann tensor, we know if we swap A and C, it's antisymmetric, we'll pick up a minus. So if you switch A and C here, you'll get C, B, and AD, which is what that is. And similarly, if this will turn into that, so you can just see by eye that by switching A and C, this will turn into a minus. Similarly, you can switch B and D, and this again will flip and pick up a minus, or the two grouping. It's pretty quick to check. Why we care about that is because if I take another partial derivative of this, as we know, partial derivatives, they commute. I can switch them back and forth, whatever order I want. But these are symmetric, but I know these indices are antisymmetric. So even if I take just BD here, this is something symmetric by something that's antisymmetric in this symmetry. So we know it has to go to 0. Okay, what that means then is I can take the partial derivative of this, which is like taking the partial derivative of this, and this is equal to 0. And now this is starting to look like a conservation of energy momentum pseudo-tensor, which is exactly what it is. Okay, excellent. Next. Okay, the next thing I want to do is introduce the harmonic coordinates in a slightly different way than Martha did. So what we'll say is the partial derivative of your Gothic inverse metric is equal to 0. And then we're going to introduce the potential that we just say, I'm not necessarily saying it's a metric perturbation yet. I'm just saying it's the difference between the Minkowskian metric and my Gothic inverse metric. Okay, but if I take the partial derivative of this g, of everything in this equation, this is the Minkowskian metric, so this is just going to go to 0. So if the partial derivative of this is 0, and I know that's 0, then the partial derivative of that is 0. Okay, so now we have, what was I doing here? Oh, yeah. Yeah, okay. So the next thing you can do is if you actually just take look at this format here on the left-hand side of this, okay? And I take two partial derivatives of this. And I'm rewriting, I'm going to substitute my, there's only these tiny little white chalks. Sorry. Oh, Jesus, yeah, okay. Okay, much better. Okay, so like if you have like, okay, so you have H, A, B, wait, yeah, okay, it's just right here. We have our GB, GCD minus G, I think this is AD, G, BC, yeah, thank you. Okay, now if I'm going to throw this in, each of these is just going to become, it's going to be a, okay. And if I multiply, if I'm taking two partial derivatives of these, I know, okay, obviously I'm going to have eta squares, I'm going to have eta by h's, and I'm going to have the h squares. Right, so the eta squares, I know if I get the partial derivative of those, they're going to go 0, so I don't have to bother with them. So I can just take the partial derivatives of when I have the combos. So I'll have like eta AB CD. Okay. HAB. Then I'm going to have the opposite. CD. Wait. CD. Okay. If I do something stupid, just tell me, because I'm super sleep deprived. CD. Okay, so those are the cross, and then you're going to have minus, okay, eta AD. What am I doing? CD. HBC minus CD, G, AD, eta BC. Okay, and then I'll have the quadratic ones, which will just be H, AB. And when I have HCD, if I take say the D, this will only hit this one because obviously I'm going to have my, my harmonic coordinates, so I don't have to worry about that term. And same when I hit the second one, sorry, CD. And then we have, wait, that's plus, okay, that's minus, and then you have the C will hit this, and if it hits this one, it just won't work, and then the D will hit that one. That should be H, sorry. It should be all H's. Okay, does that look right? Hopefully, are people following? Okay, and then what do we do? Okay, this is my I have okay, this one is this. That's the CD, the AB, those are there. And then, how do I kill these again? Oh. Yeah, this goes obviously because it's a D contract there. This C and the C, sorry, that's gone. I should have noticed that. I told you to tell me if I was doing something stupid. Okay, and this is, what's my box? No, it's not. That's my box. That's my H. Right. That's my box here. Yeah. Oh yeah, this is gone too. Jesus Christ. Okay. Okay, grand. Oh, that was soul destroying. Okay, so we have our, and we pick up a minus which I've completely forgotten about. But okay, so we have our Dalbertian, and then we have our two extra terms here. Excellent. Let's not do anything else on the board. Okay, so that means then we've rewritten the left-hand side like this. But I've also kind of grabbed this down here. And then what we can just do is rearrange all this, right? So I throw my box over here, so now it's positive. I move this guy over here, so now it's negative. And these guys stay here. So this is just simple rearranging. And then what we do is we just say, okay, well, this is part of my H potential. And I'm just going to relabel it with something else that looks like a source term. And now I can write everything as a nice, pretty wave equation. And Martha did mention this yesterday, saying that there is a stress energy pseudotensor that can be written in this way that can be helped to get higher harmonics. Okay, so there's your wave equation. Okay. Okay, yeah, and also then obviously what you can see is we know from here that when we take the partial derivative of these two guys that you're going to get 0. But we can also see if I take the partial derivative here. So if I do a partial derivative of B, it doesn't hit here because your harmonic coordinate gauge or Lorentz gauge, it'll only hit this term. And similarly over here, it won't contract with this, it'll contract with this. And then what you could notice is that actually if you switch the B and D indices, because they're both dummy indices now, these two terms are identical and it'll go to 0. So you end up with a really nice, simple kind of conservation equation.
Why is it a pseudotensor?
Because it looks like a tensor, but it's not a tensor. It's scaled by scalars, by factors of the metric, of the determinant of the metric.
So if you change the signature of the metric, you would gain a minus sign or something?
No, it doesn't behave perfectly as a tensor.
Under coordinate transformation.
Under coordinate transformation. Define a tensor. Okay. Okay, next I'm going to go into Green's functions. These again was briefly mentioned by Martha, but because I'm going to talk a lot about Green's functions today, I thought I'll go over it just again. Okay, so now we have a wave equation. Yay. And hopefully some people are familiar, or all of you have seen wave equations like this, where you use the idea of a Green's function. Okay, so the Green's function, you just say the solution of this is an integral. Oh God, I used 2 G's. You're supposed to be a plus here. Okay, you just basically take whatever your source is, you throw a Green's function beside it, and you integrate over the 4 space, and that's going to be your solution. Normally this should have a plus, because then it's going to be the retarded Green's function, and that has to satisfy this. Okay, and if in doubt, you can actually see this by I, because if you think like, if I just get this operator and throw it on H, and this is acting on X, not X prime, right? So you throw that operator, it's only acting on X, and the only thing that's a function of X in here is G. So this hits G, and you get minus 4 pi delta. So your minus 4 pi comes out, and you have your minus 16 pi G over C4. So that comes out straight away. And then you're integrating over a delta function, and hopefully people are familiar with the idea that if you have a delta function like this, X minus X prime, it's basically saying the only time this is non-zero is when these are equal to each other, and you can effectively just make everything that has it converts everything that has, you basically set X prime to be equal to X. So if you have a delta function against any kind of function of X prime integrated over X prime, you just set X prime to X, and that gives you our pseudotensor. Yeah, sorry, so this should be G plus here. So G plus is the actual Green's function. This G is the gravitational constant. That was my bad. Normally you'll see it with a plus or minus, meaning it's either retarded or advanced. And the idea of that is, and I'll be touching on this with the self-force, it's this whole idea that if you have a point in time, you can have incoming radiation on its light cone and outgoing radiation And then when you're looking back to things that are hitting this, this is kind of the retarded, and this is the advanced. You're saying, okay, this is going into the future, and this is coming in from my past. Okay, so
maybe is it true to see the Green's function as the solution of your wave equation for a point source in space-time?
Yeah.
Basically.
Yes, exactly. Okay. So what's really annoying about today, I noticed is that in all the post-Newtonian stuff I was working, these things are actually different. But for post-Newtonian, and to self-force. Okay, so for post-Newtonian, our field point is going to be x. So, and our source point, the thing that's either radiating, is going to be x prime. So the idea here is you would think of, let's not go like that. So here's my source. It's radiating energy. And say here's my field point. So this is x prime. My field point is x. And it has hits like cone. Doesn't have to be exactly whatever. Okay, so this is now in its past. You can see this radiation. And this is, what was I? Yeah. Okay, and so when we look at what this person is seeing, they can say, okay, I can have incoming radiation, or the same solution can also be outcoming radiation from here. Or you can flip it and do it from here. Okay, so, okay, for flat space-time, let's keep it nice and simple. And there's a very well-known solution. You can get it by doing a Fourier decomposition, which I'm not going to do. Take my word for it. The solution is a delta function over the difference in your time minus the magnitude of your spatial distance, which sometimes is just written as r, and over, like, multiplied by 1 over r. Another way of writing this is this here, and just to convince you on that, because I'll use it also for the self-force, is that if you think of, you have delta, what is this, ct minus ct prime squared minus x prime squared. Okay, I can say that's delta of ct minus ct prime minus x prime by ct minus ct prime plus x minus x prime. And this is all in my delta function. And say I'm like, okay, I'm thinking I'm going to take the retarded solution. So I'm going to say that this is greater than 0. And if this is greater than 0, then this whole thing has been greater than 0. And remember, for your delta, you need one of these things to be greater than 0. So this can't be greater than 0. We just think of it as something multiplying it. And you have this formula that if you say a delta ax, that's equal to 1 over, as long as it's positive, delta x. So we now know this is something that's going to be positive. So while you can kind of think of, if you're integrating over this, that now for this to be non-zero, ct minus ct prime has to be equal to x minus x prime, which means this is now delta, well, this is actually, we're going greater to 0, but it's actually equal to 2x minus x prime. Okay, now I have 2 minus x prime over this, so this is just going to be ct minus ct prime minus x prime divided by 2 x minus x prime. And then I have the 2 above here to cancel it out. And I'll be left with this. And the step function is just, it's telling you if you're retarded or advanced. Everyone knows steps. Yeah, so that, like, it's just equal to 1 when this is positive, and when it's equal to 0 when it's negative. Okay. So what this means is, it's a wave equation. We now know how Green's functions work. We know what the flat space-time Green's function is, so that means I can always solve for my metric perturbation by an integration over this delta function, 1 over r in the bottom, against my, my source term, integrated over support 4 space. Okay, and then what we can do is, ignore this 4. This d4x is over 4-dimensional spacetime. So we'll integrate over t prime. Okay, so we have a delta function with a t prime, which means now my t prime will be set to ct, well, divided by c, so it'll be t minus x bar, well, x minus x prime over c. Okay, so now this, this is at the moment a 4 point or whatever. This is now going to be your time, t prime, we've now set to t minus x prime, and then we just leave the 3 vector here. And then we haven't done anything to this. So now we have a way of solving for our metric perturbation. It's no problem.
So what's the physical interpretation of the field point and source point? It's just one is in the future of the other, or?
Sorry, say it again?
What's the physical interpretation of the field point and source point?
Oh, yeah. Source point is the thing that's emitting radiation.
Okay.
It's the source.
Oh, yeah.
And a field is just me with my detector or something that's going to be able to observe it.
Okay.
So the field point is like you think of someone being in the field, I guess? I don't know. What? Okay, yeah, a probe. So something that's going to be able to detect it. So yeah, in the field. And the source point is whatever's radiating it. So in our case, this is a gravitational wave.
That makes sense. Okay.
But this all works for electromagnetism as well. So this is all done out in electromagnetism years ago.
Okay. Thank you.
No worries. No, ask. Okay. I messed up my builds. Okay. What happens when we actually want to integrate these things? Okay. Okay, I won't go. I had ideally hoped that I would be able to go through this in great detail, but I gave up partway through because I started losing the will to live, and I imagined you guys would too. So basically the idea is, okay, if you're integrating, your metric is going to be integrated over, because you're integrating over your light cone. So what you can do, so this is my source here. And that's whatever is emitting the radiation, an electron, a gravitational wave, like a black hole binary, whatever. And this is me with my detector. I'm integrating over this light cone. And what I can do is I can split it into 2 areas, because we can always do that with integration. We can go, this integral is a plus b. So we often split it into the near zone and the wave zone. And then we say the metric of the near zone or wave zone is just the exact same integral we saw in the last slide, but just you're changing your integration domain. And then the full HAB is actually the sum of these. So you're just splitting into this whole cone into a little slice here and everything over here. Okay, and then you have to think of 4 different scenarios. So the first one is like you're integrating over the near zone, but you're far away here. And the idea is that you can introduce a kind of dummy derivative, or a dummy variable. So I can always kind of add an integral with a delta function and over a 3 space. Because I know if I integrate this against this, I just set y to be x bar, and I can set my x bar to be y here. It's a bit of a cheat. And then I say that because I'm only integrating over the near zone here, anywhere I move from here, this x prime is going to be very small. So I do what we all love doing best, and I Taylor expand. Okay, so basically this is just say, there's my x minus x prime, so that's a 1 over r. My derivative here is hitting this whole thing here. So you do the Taylor expansion before you kind of do this integral, but I meant extra lines and I didn't want to write them. But the idea is that you Taylor expand around x bar equals 0. And so then this becomes t minus x bar. This becomes just x bar here. You've dropped off your prime, which is why it gets out of the integral. And then you're differentiating with respect to x bar. Originally, because you're doing with x prime, you start off with a differentiation with x prime, but then because everything divides by x prime and x prime, you can flip to the other x and bring in a minus L because they differ by a minus. And then, so this is just how many derivatives you're taking, and as you know, to the power, it'll be like -1, then it'll hit a -2, divided by 2, 3, so on. Okay, and we have our 4G over there. Okay, now that we've, and then you integrate your delta and set everything back, your y back to x bar. Okay, and what we've done now, notice, because we've gotten rid of this x primed here, this is dependent on t minus x. You can think of t is here and x is kind of like your distance. So this is actually a constant time now. So we're not along this curve, now we're along this surface. We're along this surface. And then if your thing is really far away, you can simplify this more. You just call this your retarded time, and you change this derivative into the derivative of your retarded time. Okay. Yeah. Oh yeah. This is really annoying. Yeah, sorry. It just means that so say okay, say if L for L equals 1, you have say dx. You might have dc prime, and the thing will be contracted with c prime, and then the next one will be say c d prime, and you'll have x c prime d prime. And what we start doing is we call this L.
So, typical L could be.
So it's a whole load of them. So when you get to the third one, so for the next one, then you're going to have 3 derivatives and multiply. It's a Taylor expansion, sure. You know the way. But just it's a good question. It's a notation in PM. They use it quite a lot. And spherical harmonic decompositions. But yes, thank you for reminding me. Not everyone's used to it. But it's literally this idea that you're building up all these indices, and nobody wants to write all their indices. So just go, okay, if it's 2 here, there's 2 indices here.
And what does the xc prime d prime mean? Sorry, actually, is it like xc prime x times x d prime? Sorry.
Oh yeah, that's another thing I always do. Yeah.
Okay, cool. Thank you.
It's because there's so many indices, we're always using these shortcuts. Okay, so that's the idea of the near zone. Okay, if we do so this was, the last one I just did there was near zone integration but the field point was far away. But you can also have a near zone integration with the field point in it. And again, it's just you Taylor expand something else. So this is the trick that you play. You just write out the integral and you're like, what can I make small? Taylor expand. And I think there's a minus wrong. Oh yeah. So for this one then, again, you have this integral here. We're Taylor expanding around x minus x prime. So if you think of this function here, okay, I set my x minus prime to be 0. I'm only going to expand this. And then you take you have the 0 derivative. And then you have the next derivative, and that'll pick up an x minus x prime, which cancels with this one. And you go on and on. And then another way, shorthand, to write this again is because of this 1 over x minus x prime, you're going to have an L minus 1 with your little thing that you're multiplying out. You pick up a power of c and a minus 1 because you switch which one you're differentiating with. Anyway, the main idea is to see that, general gist is we have our integral. We look at each different scenario, we find something small, we Taylor expand in it, and we get a different integral for it. And then everything has to be added back up later. Okay, then the next one is then if you're integrating over the wave zone.
Just a quick question.
Yeah.
Thank you. The previous near field point, in gravitational waves, when are you going to have a probe that's right next to it?
Good question. Because sometimes what you actually want to, your detector's not going to be there, but you need to calculate the field there because sometimes you can emit radiation, it can whip around, come back and hit you. Okay. So you can have these scattering effects, which is why you always have to be integrating over all the space-time. And then that obviously affects your movements too. Okay. Yes.
So can you maybe just repeat again what this picture shows? Where's the source actually in the...
Keep asking. It's good. I always forget it too. Okay, our source is here, and this is here either with our detector or whatever we're trying to find out, which is what led to your question. Because you're like, yeah, my detector's not going to be here. We'd all be dead. But, but you still need to know what's going on there because you have to get the fields for the whole space. So what you're doing is you're moving your x all across the place and being like, okay, when I'm here, it's going to look different. When it's here, I'm going to look different.
And then you had some other picture where suddenly you were somehow in a different plane.
Yeah, okay, that can, crop, sorry, spoiler. No, what is this? Shoot, sorry. This.
Yeah.
Mm-hmm.
Yeah, so originally you were kind of, when you're integrating along this light cone, but then when we were doing this Taylor expansion, remember this is the T component of the source, the time component. Okay, so it was, you can see it as T time here minus the difference between these 2 points, which will kind of set you diagonally up here, whereas T minus X is going to be your distance from here, and T instead, these are constants, they're not varying, so it's a constant time.
So you are saying that in the Taylor expansion, the integral over the horizontal surface is approximately equal to the integral over the...
Yeah, well, you've kind of changed what you've changed everything else to kind of agree to it. You're kind of saying these things are equivalent.
I mean, they are small and therefore they are... Okay.
Yeah.
I get the intuition.
Yeah.
Thank you.
No worries. It was... Go.
Sorry. I think I remember seeing sometimes like cosmological zones. So like, do you take into account the fact that space-time is stretching or...
Oh, God, no.
No? Okay. Okay.
Somebody else's problem.
Okay.
Okay. So then we go with that. Okay, so for this one, I'm not going to go through how we get there. I'm just going to kind of let you know this idea exists. The idea here is that you have all these different scenarios that can arise. Because the idea here is now we're integrating over the wave zone, so we're integrating here. So we have to see the radiation emanating from here and where it hits the cone. And depending where this intersection lies, so this can still be far away, but my kind of world tube of my source could still be within this surface. Or maybe so this is the light cone of things emanating out of my source, and this is the light cone of things I can detect. So if this is within it, you can, that changes you have to split up the limits on your integral. You could also have that actually, where these 2 cones intersect, actually dissect it, or they could actually just lie perfectly on top of each other in this scenario. And you have to combine all different 3 situations. I won't go into how you do this. Spoiler, Taylor expansion, spherical harmonic decompositions, and that's the functions there. And then, ignore that for a moment. Then the other point then is when you have, when your field point is close to the source, so this scenario where we want to see what's going on close to the source, you have these 3 different scenarios, and you can do the whole equation again, but basically you just end up changing the limit on one of your integrals. Okay, so the whole point is through all of this, we split we know we can get our metric perturbation by doing an integral over space-time. And then to do that integral, we realized we have to think up 4 different situations because we love Taylor expanding and we always want to find something that we can Taylor expand to make our life easy. Okay, right. Now what does it look like when we actually do the PN? So the whole point of that was just to prove to you that like once I have a source term, I can integrate it and I can get out my metric perturbation. Yes?
Sorry, maybe super naive question actually, but like why, because we could do this whole thing, why do we have to use the harmonic, sorry, I already forgot the name.
Oh yeah, there's different gauges that other people use. There's lots of different ways of doing this.
So why quote unquote bother and work with this tau
because it's
AB?
one way of solving the equations.
Okay.
Yeah, but there are different ways. So
Okay.
actually in
So PN doesn't rely on
there's a harmonic and the ADM gauge, isn't it? Yeah.
Oh.
There's another gauge as well, and those are the 2 kind of faves.
Sure.
And even there was all this whole issue that when they got into higher and higher PNs, they started realizing there's things that they weren't being able to constrain, like gauge freedoms that they shouldn't have had, and it was this whole debacle, and eventually they figured it out. So it does create a mess, but the point is you use your gauge freedom to just make your equations as simple as possible.
And the Lorentz gauge, for example, is not simple. Why not use the classic Lorentz gauge or?
Well, this is actually ends up being equivalent. Yeah, it's
Okay.
Yeah. So this is the harmonic gauge is equivalent to the Lorentz gauge. It's just it's kind of rolled out in a different way and structure, but they're essentially they're essentially the same.
To do PN, do I have to use this, I guess?
No.
Okay.
This is just, I did a postdoc with Cliff Will, and this is the way he does it, so that's the way I learned how to do it. So, but I mean, I think there's actually faster ways now from the Paris groups. Yes, behind you.
Yeah, so just something I probably missed. You're talking about metric perturbations, and we are solving a wave equation for HAB.
Mm-hmm.
Now, you introduced HAB as something with the Gothic
we're
thing,
coming
which
back
is not a tensor.
Someone's got their eye on the prize. Yes, we're coming back to that. Okay, don't worry, that is coming. Okay, so then basically, for now we're forgetting about that, but we're just going to see how do we solve our PN. So the idea is, I start off with my flat metric, the Minkowskian. It's lovely, very easy. And I calculate my source term using this. So I can calculate my source terms based on what source I have. But when you're doing your source, you're always going to have your metric in there and whatever way you're defining whether you're having matter, vacuum, or whatever. Okay, so that's kind of like a 0 PN source. Then what I do is I go, okay, but my metric, I'm going to add on a perturbation here. And I have a source term, so I can put my source term into my integral, and I can solve for this metric perturbation. Okay, then I put that metric perturbation back into my equation for my source term. This is now higher, it's more complicated than my Minkowskian, and I get a more complicated, higher powered source term. And then I put that back into my integral to get my next order. And you basically, around you go.
Why 0.5?
Oh, because you can go, because 1 PN it's a V squared over C squared, and at some stage you start getting half PNs.
So V over C.
Yep. And basically, around 2.5, you get radiation reaction, and from then on, you start seeing half PNs. Okay, that's the basic idea. Okay, so what I thought I'd do, this took way longer than I thought. Okay, so I thought I'd do a perfect fluid. So you have your energy momentum tensor for a perfect fluid, and a rescaled mass density. So basically, we just have our usual Lorentz factor. Okay, and then what we can say is, okay, well, when I start off, my metric is going to be Minkowskian, so this is just 1. And I'll just Taylor expand out my gamma. But gamma here is the power of -1, so this is really power at half, so I get 1 minus a half V squared over C squared and higher order terms. Everyone see that? Okay, then we go again, su and eta. What happens here? I have my T00. I have C squareds here, so they're going to be C to -2. My UA, UB, if this is 0, 0, didn't put it up, but you can say like UA is equal to gamma CB. Is it? Or is it the other way around? Sorry, I'm completely brain dead right now. I think I wrote this down somewhere. I think that's right. Yeah, it is. Yeah. Okay. Sorry, I'm super sleep deprived. Okay. Okay, sorry. So when we look at the T00. Okay, so with T00, if this is U00, I'm going to have gamma squared C squared. Okay, so that C squared, I just pop it over here for now, which is why you have a C -2 here. And then I have my expansion here. So this is just going to be rho star, and then I have powers of C2, C to -2, here's C to -2, C to -2. So I don't care. And this is going to be eta 0, 0, which is also going to have a C squared. So we end up just with the rescaled mass density. Okay, if I take a J, now I only have one C here and a V. So I end up with a Vj, and that's why I only have one C minus over here. And then if I do Tij, okay, now I have Vi Vj here, so I don't have any C squared, and I can see that this is of order 1. Okay, so when I look at my tensor density for a perfect fluid, I can see the leading order here, and that this guy is going to come in at a higher order. Let's go back to those equations we derived where you got your metric perturbation against your tensor. And you might be going, wait a second, this is a tau and this is a t. And that's because, yes, remember we had the Landau lift shift tensor, and then we had the tensors that came in from the harmonic gauge. But they were all coming in with a power of a h, which has a power of the c squared. So for the first order, we only have to worry about actually our stress energy tensor. Okay, and we literally just throw these into here. Okay, for 0, 0, it's just going to be a rho star over r and over your over your 3 space, and then higher terms. And then this, we just say we've recovered our Newtonian potential. Very long-winded way. The next one, OJ, again, it's just going to be this term popping in here. And then we say, okay, that's our mass current density, and we have our vector potential. And then for the next one, for now, we just say it's higher order. Don't worry, I'm not going to go to a higher order. And then the nice thing to note here is that we can see the H00 here comes in at c squared, 1 over c squared. And here c to the minus 2, c to the minus 3, and c to the minus 4. Okay, so this is the dominant term here. And then we come back to what we've been brought attention a little bit earlier. It was actually, remember, it was the Gothic inverse metric that our H was described. It wasn't the usual H even. So what you have to go back is say, okay, well, if this Gothic inverse metric equals this, I can get my normal metric by calculating this. So basically, you throw this into this, and you Taylor expand it. And you get this. Just take my word for it, or all the books that have it in it. Okay, and then if you actually put in the 0, 0 here, 0, 0 here, okay, this is going to be a minus 1. And then you can see, oh, did I miss the wrong? Oh yeah, sorry. You're using the eta, remember, is your base metric still. So you can say HAB is equal to eta AB HBC oh Jesus, eta B C B D HCD. Okay, so then if I want H00 of this, I can say that's eta 0C, eta 0D, HCD. We all know that the only thing this can be then is 0. This can be 0, which are going to be minus 1 by minus 1, which is 1. And that means this is going to equal to H00. Okay, so you go through them all like that to get out these. Okay. Then we go back to the H00s that we had figured out, and we throw these in here, and we call it c to the minus 4. And you basically get your first PN, and only for that particular scenario of the integral that we looked at. Remember, you do have to do the other ones, but this is the one that comes in at the lowest order, which is why I did it. The other integrals come in higher. Okay, that's how you do PN. Okay, that's one way of doing it. There's lots of other ways. Okay, so now that you all understand in your heart and souls how PN works, where are we in the world of PN? Not bad is the answer. Do I have? Yes. Okay, so what the hell does all this mean? Okay, this is my PN order. So this is like my V squared over C squared, and these are the half terms of the V over C when you have the half. You have dynamics, and you have the dissociative flux, so things you're radiating out. Okay, for the non-spinning case, we're all the way up to 4. And these ones are just partial results. So sometimes you can get out something with a different perturbation, or they've done part of one of the integrals but not the others. Yes.
Is this all analytical, or can you use some numerical tools to help you? Sorry, is this whole like done analytically, this work?
Yes.
Like 4.5? And can you not use any I don't know, like
yeah,
very naive question?
You can. And actually, that was a game that people started playing with self-force, where they started re-expanding self-force thingies in post-Newtonian and then solving numerically, and then doing it to such a high accuracy they were able to read off, and they knew what the structure of the PN coefficients could be. Like they're like, oh, we know there's a log or there's a pi to this power, and started being able to actually figure out what these coefficients were. So you can, but the idea is you want to cut down on computation time. So if you can do it analytically, do it, because you have it for everything. Okay, but actually when you do eccentric, which I didn't have time to go into, but a lot of the time the way you bring in the eccentricity, you recast your equations into like a kind of Keplerian, quasi-Keplerian way, and then normally you end up with ODEs that have to be integrated.
So like 4.5 is all pen and paper? No way. Wow.
Yeah.
Okay, yeah,
Yeah,
thank
yeah.
you. Yeah, so I guess I was getting my question, and nice mathematical.
Yeah,
okay, of course. Yeah.
Mathematica. Gone are the days of Maple. Okay. Okay, for spinning, then you have spin coupling, so the spin of your body to the orbit, the spin-spin, higher terms, and the same here. So you can see like everything is moving along, but I think they almost have 4.5 PN out now. The PM research, and then you also have the PM, but both communities are really active and they interact with each other, and there's this whole thing about using scattering amplitudes and effective field theory, which I'm not going to go into because I don't really know too much about it, but it exists. Okay, and then there's a big challenge that people are scared of at 5 p.m. because then you have to take in your finite sizes. You can no longer say this is a point with moments. You have to really get in the finite size and tidal effect center, and things get complicated. Okay. And why it's really, really important, one of the main things for LISA is those, remember yesterday I said you have these massive, supermassive binaries, which are like colliding galaxies, and we could see them for maybe a year in our detector, depending on their mass. You can have hundreds and hundreds of cycles, and you can't do that numerically. So you will need to stitch a PN into your numerical simulations. Okay. Yep.
So I've
No.
finally
Students first. No, go on. It's fine.
No, go.
Sorry. I finally understood how PN works, but I'm not sure I understand, because you've expanded everything in terms of V squared over C squared. How do you do the post-Minkowskian on top of it?
Well, at the start I was doing the post-Minkowskian. I don't know if you noticed. So actually when we did the Gothic one, you actually say that first perturbation is in Minkowskian.
Right.
And then we re-expanded in post-Newtonian. So this one actually does both of them, the way I did it. But there's ones that don't. So there's different combinations of doing it.
But so if you want to be exact, then you have to do the next order in post-Minkowskian and then redo all your order in PN?
I don't think so. But I'm not sure.
Okay.
I don't think so, though. But if you really want to know, Cliff and Claire Poisson wrote a book, and it's all done out in that. Just a quick 1,000 pages. Oh, yeah, sorry, question.
Yes, I was wondering how many orders of PN do we expect to need for the next generation of detectors? Like, is this 5.5 if we figure it out enough? Or?
Basically, the more you get, the better it is.
Oh, okay, yeah.
So you can even see like graphs where a lot of times when they're comparing numerical self-force and PN together, you'll see like it's super crazy. Like you can just say it's something like maybe self-force, like you maybe have maybe something that goes like this, and you'll see the PN PN terms are going like this. You know the way, so you can see that each extra thing is getting you that further.
Yeah.
Right. And then recently people have been using little like resummation techniques and things like this. But there is a point where, it's diminishing returns.
Okay, yeah.
But I think as far as waveforms are concerned, the more you can do analytically, the less you're going to have to do computationally.
Yes. Thanks.
And if you have to work out to hundreds and hundreds of orders.
I have a question. Are there any Okay, so there's a lot of work to actually do these calculations, but are there any things that would actually limit you at some point in your expansion orders of v squared over c squared that you would say, this is a point I cannot go beyond? Like there's a
Yeah, so
mathematical fundamental barrier.
So yeah, like I've heard Eric Poisson talk about 5PN a lot and how they're not convinced yet of the actual foundations.
So that might be a point where the post-Minkowskian might be a better approach with the scattering amplitudes, because they would claim that they can do their
you've affected field theory as
field
well.
theory,
so the idea is that hopefully you can
order.
mix these things together in as much information as possible. And I'll show something that's really cool later that really shows why doing these things is still important, even if you don't get the full result. But yes, I have heard people say there is a fundamental obstacle that they have to come over. You can't. It's not like I said. Like you just Taylor expand. It's not. Even 4PN took years and years and years because they realized there was some extra gauge issues that they just hadn't thought of. And then when two different methods gave different answers, there was a little war. And then they realized why. Anyway, okay, so that's PN. Now to cell force, which was, I thought, going to be the longer part of this lecture. Dear Jesus. Okay, so what's the cell force? The cell force is also a metric perturbation. Okay, except now the perturbation is in the mass ratio. So now we're back to looking at this, the little mass over the big mass. That's what we said yesterday. If we go back to our Einstein field equations, the way we look at it in the self force is this now is the metric of your full space-time. And not Minkowskian, our background space-time is actually going to be the background black hole, so Kerr black hole ideally. And then a perturbation from the existence of this person in space-time. Okay, so the full Einstein equations will be of this kind of super fancy combined metric, which then we linearly perturb. Okay, so then again, if you just do a linear perturbation of your Einstein field equations, we're saying that because we're saying this is a Kerr black hole, our only mass in the system is coming from the little person, which is why you have an epsilon here as well. And we know that we're going to have, for a Kerr spacetime, this will go to 0. So this is the equation we're looking at. Hopefully people have linearly perturbed the Einstein tensor. Right. Oh no, that's not a button. If you do that, you get your wave equation, you get a Riemann tensor popping out, and a load of covariant derivatives. Okay, and then on the right-hand side, you have your test. We do the Lorentz gauge. They're like pretty much equivalent. I'm not going to say exact to a harmonic gauge, which is just when it's there's a contraction with its covariant derivative. Okay, and then we have a wave equation, but now it's a different type of wave equation. Okay, so I said our stress energy tensor now is coming from the little one. So we have our action for that, and from your action you can always get your stress energy tensor. Okay, once we have that, then we want to get our equation of motion. Okay, Martha touched on this yesterday. I just put up the stress energy tensor so you remember what it looks like. Okay, well, we use our conservation of energy momentum. So I get the covariant derivative of my stress energy tensor. If I hit this, this is hitting x, so it's really only hitting this term and this term, and there is a formula that then allows you to move that into a partial derivative onto your delta function. Take my word for it. And then we move our derivative back onto this side and using divergence, and that I'm dropping one of the 4 velocities. Okay, then what we have here, if I just, sorry, some of my colors aren't great. Okay, and then basically what you end up is this can be rewritten. Wait. Oh yeah, sorry, you hit this to this. Okay, so you're hitting the lambda prime onto this. Okay, so you basically get, you're going to hit this, you're going to hit this, and you basically get a mixture of Christophel's and the derivative. This is just a derivative of the thing underneath. So you can see that if I hit this, I'm going to get 1 over it by the derivative of that. Okay. Okay. So I would have time going through these more precisely, but I clearly don't. But just take my word that there is a to here. The reason why we rewrite it in this way is because this is equal to 0, which now means this is equal to 0. And I can rewrite this, because this d is in the background metric, which are these Christoffels. So I convert it into now derivative of the covariant derivative of the, oh my god, my brain, of this background. Okay, so this is the full, and this is of the background. And you're just basically getting the difference between the two Christoffels, and then you have your k term there. So in perturbed spacetime, we go back to our k, and if we work it out, because we put in our 1 over thing, and we're going to get the derivative. So you basically have, this minus GAB by that's just going to be your 4 velocity. This is going to be your GD6, your orthogonality of your 4 velocity, Jesus Christ. Okay, so it'll give you a -1 plus your perturbation, and same here. You're going to have your -1 by minus, and your perturbation. And then if you hit this, obviously you can perturb this out. You're not going to, the 1 isn't going to differentiate, and you're just differentiating this. And you can rewrite that again as this. Take my word for it. Why this is cool is because this basically is telling you that at 0 order, because remember, this is at order epsilon. So at 0 order, you didn't get anything. You just got a 0. And the first term you got is going to be your A, which you rewrite this from this. Sorry, I meant to go through all this on the board, but we actually just don't have time. What I might actually do at a later date is put the steps in between, or as an exercise for the students, you can see if you can do it yourself. But take my word on it. But basically you end up, the idea is, because this ends up at a power epsilon, you know you get a 0 at the 0th order, which is exactly what you expect because it's a curved geodesic, so you have no acceleration. But the point is, once you linearized and added this as a perturbation, that introduced a first order acceleration, which you could see as a force, and that is why it's called a self-force. Because when it was a test mass particle, so something that we just pretend it doesn't have a mass and it's going around, and this goes to 0, but the minute you say, no, this is actually a black hole and there's stuff going on here, now all of a sudden you have an acceleration. So it's caused its own acceleration, which is why we call it self-force. What time do I keep talking till?
15, 20 minutes? 20 more minutes?
Okay, let's go. Okay, so back to this. I'll just go quickly because we saw this yesterday. It's a linear perturbation. Okay, when we're doing the self-force, the main thing that we talk about is, you might have heard people talk about first order self-force and second order self-force. And that's literally like the linear and the quadratic on the perturbation. Now, the good news is, for the first order, the linear perturbation in Kerr, you use Jokulski, which I think Martha might mention later. There's a good handle on this for almost all systems. So this has been calculated, even for generic, but only once. And it took 3 months. And no one went back to it. Because people are like, let's do this smarter. But there's methods there now. People are trying to figure out better and faster ways of doing it. So this problem, there's a good handle, but still lots of work. Because also, like I said, there was different ways of doing the post-Newtonian. There's different ways of doing self-force. And ideally, you want to do the calculation in completely different methods and get the same answer. So everyone's always coming up with new methods. The second order is difficult, it turns out. The first, if you actually even track the papers on this, I think it was 2012, when people first started talking about how they could even broach the problem, because the theoretical foundation of how you could even do it just didn't exist. And there was like 3 papers within a few months saying how each person thought they would do it. And in the end, it ended up being a combination of the techniques each of them outlined. So that was 2012, and the first waveform came 9 years later. So from when they first started conceiving how to do it, it took 9 years. Okay, and it's only been done for Schwarzschild circular. Okay, so remember when we said you can build the complexity of your waveforms? Schwarzschild circular is Almost as simple as it gets, but actually in self-force we figure out even simpler ways. Systems. Okay. And then remember, it's a force, right? So actually, the idea when you think of it as a force, even though it's not really, it's an effective metric, you can think of like, you have a point in time. Okay, say it's here. I have a point in time. I calculate the self-force at that point. And that tells me I'm not going to follow the geodesic, the test mass geodesic. I'm going to be pushed off it. So now I can calculate how much I'm pushed off this geodesic. And now I have to calculate the self-force at that point. And see how much I pushed off this geodesic, and so on and so forth, right? And that's this idea of self-consistent evolution, hugely computationally expensive, but that was one of the first ways of thinking how we could do this. Okay, so you need to evolve your orbit. As it turns out, there's some multi-scale tricks that you can use to avoid this scenario. But the idea is maybe you want to do this once just to check that they work as well. Okay. Just go a bit pressing. Okay, so like I said, in 2021, but it was at Christmas, so it was really 2022. They got out the first self-force waveform. Okay, and what is really cool here? I'll talk about. So here I talked about first order self-force, second order self-force. You also might hear people saying adiabatic and post-adiabatic. I'll explain that in a second. But the idea here is the yellow, the post-adiabatic requires the second order, but it doesn't require the full second order. Okay, so you have, the yellow is the post-adiabatic, and the blue, when they zoomed in on this area here, is the adiabatic. Okay, so you can see if you don't get your second order self-force to get the post-adiabatic, you will have dephasing. Quite a lot. You can see within a few oscillations it completely dephases. Yes?
Sorry, I didn't quite get how you went from like a force to the waveform, like how...
Oh, I'm going to explain it in the next slide, don't worry. Yeah. Because actually, in reality, they don't actually use the self-force when they calculate the waveform anymore. Like this is an idea of how to do it. You calculate the force, but actually they use some scaling arguments to make it easier and more computationally efficient. Okay. Is there anything else I wanted to say here? Sometimes, oh yeah, but I talked about this yesterday, so that's fine. Just ignore it. Boom. Okay. So if we think about, hopefully everyone here is familiar with Kerr GD6. So the way that they do self-force now, so they don't have to do this every single thing, is, okay, we can think of a test mass on a GD6 and Kerr space-time. One of the ways of looking at the system is you have your three constants. They're characterizing your geodesic. Your energy, your azimuthal angular momentum, and your Carter constant. Okay, and when you do these, you can see these are complicated orbits, right? It's not these circular ones like the video I showed you yesterday. They have this kind of zoom whirl where they go in, spin around, zoom back out, slow down, and go back in, which also is why it's complicated for post-Newtonian, because as you get closer, you speed up, and post-Newtonian has that risk of breaking down. And then you might zoom back out and still have a buttload of orbits to go. Okay. Also, in the scenario for your r, theta, phi, you're going to have phases, and each with their associated frequencies. And you use this to solve for your system. And this is a completely solved problem with Kerr space-time and GD6. Okay. What happens when we want to do solve first? Okay, well, you think of it as a perturbation on that. Okay, so now your orbit description is you're going to say, well, I have these perturbed variables. So my full set of system parameters is the same as before, but now I also have to take into account the mass and the angular momentum of the black hole, because they could be changing. And I do this 2-time scale idea, and that comes from the fact that the time it takes for radiation emitted versus the time of the orbital frequency, these differ greatly, and by an order of epsilon. Okay, so you have this here is kind of more to do with your radiation, which is from your self-force, and this is more your orbital. Okay, so you have your phase frequencies now, same as before, but now things are a bit more complicated because we have more thingies here. And we look at the evolution of the slow evolution of your system parameters, and this is where the self-force is coming in here. This is the adiabatic, and that has the dissipative piece of the first order self-force. And then you have the post-adiabatic, which has the conservative piece of the first self-force and has the dissipative piece of the second order self-force. Okay? The dissipative piece is the easier piece to calculate. So the first order self-force, one part goes into the adiabatic and one goes into the post-adiabatic. And then you have the second order coming in too. Okay, then we want to get our waveform. Again, we take advantage of this multi-scale expansion. Okay, so your perturbation is still going to be here, but these are completely dependent on your J's, which are your perturbed variables. And then obviously you have your phasing here. Okay, the reality of what they do now is they solve these field equations for the amplitudes and for some functions for all given J's they can think of. And do that on an offline grid. So basically what they do is they're like, okay, this is our parameter space. What are all the combinations of these constants? Which is why they've only done it for Schwarzschild, right? Because you want to keep it, you don't have to do your Carter. You can keep it equatorial. You keep it even. So your parameter space isn't as big. And you can literally just figure out, okay, what are all the possible combinations? I work out a grid, and I interpolate. And that's all done offline, these J's. Then what you do is that feeds in, once you have these, that feeds in here to these ODEs here. And then this is solved online. So there are packages you can download that will give you the self-force waveforms. And they're called fast Emery waveforms. They just released the new one a month or 3 months ago. And it produces waveforms in 10 to 100 milliseconds. That one, this one only does the adiabatic. I'll mention the overview and later. There's two packages, one that gives you the fancier one, but less parameter space and one thing. But anyway, okay. Crap. Okay. Okay, the thing I kind of sketched over earlier was like when you calculate the self-force, I said like it's a perturbation and you get this acceleration. But one of the things that I kind of breezed by was that when we introduced the action for the particle, our little guy, we threw in a delta, which is quite common, right? But that delta becomes problematic, right? We've introduced a singularity into our system. So you've introduced singularity, you have to remove it safely without affecting the motion. And the way this done was years and years ago, back in the late 90s, when they figured out a way to do it is you have your small particle, it's world tube, and you say, this has come up, you have a near zone. And in the near zone, so the idea is if I'm here somewhere, I'm going to be overwhelmed by the space-time of the little black hole, and the big black hole is considered a perturbation, which I do by capital H. And then you have the faraway zone, so if I'm over here somewhere, I don't really care about this little guy. He's just a perturbation on the space-time that's controlled by the big black hole. Okay, which was the one that we were looking at earlier. And then to make sure that you can remove the singularity properly and you get a proper set of equation of motion, you have to do a matching in the buffer zone. That was one way of doing it. And that was the Misata. These were gave the Misatawa equations of motion. So it was Mino, Sasaki, Tanaka, and they did this as match expansions. Then there was Quinn and Wald, and they did an axiomatic approach. And actually, it doesn't really matter because this was all replaced by Detweiler-Whiting singular field, which I'm not going to talk about. Okay, so just to show you how the regularizing works in the now considered the kind of gold standard is, okay, we go back to electromagnetism, right? So you have a wave equation with your source. We have our retarded Green functions. Yay, they're back, and retarded and advanced. And they solve our wave equation. Okay, so this is how we solve. We're all sold on this method of solving, and we had the Green function out earlier. Okay, and the problem that we were talking about. So here, this is what I was saying. Now I think x prime is my field point, and x is my emitter, so I'm really sorry. Or is it? Okay, so basically, if I'm here and I'm the retarded solution is my any incoming radiation. But there's also an advanced solution which kind of causally doesn't make sense. So a lot of the time we're like, hey, but this is the realistic thing. You're receiving something from the past. Okay, But, okay, so what we do then, because this guy is singular, and that's going to mess up when we actually want to solve for our motion. Also, if you just solve anything numerically, you don't want singularities. It's the whole thing about numerical relativity, right? Okay, so what you do is, and this was done back in the 1930s, they're like, okay, well, this whole problem began because of the way I modeled my source term, but what I could do is just say, okay, my retarded solution that I've solved for has a regular part, which is the true physical field, and there's the singular part, which is the mess that I've introduced into it. And what you want to do is you want to design a singular field that you can subtract away from your retarded field, so you have a nice regular field that will still solve the wave equation, but without singularity. So the idea back then was, it was a pretty easy solution. They just was like, okay, let's get the average. The idea being that if you think about being at this point here, okay, remember this is incoming radiation, this is outgoing radiation. And I want something that's not going to affect the motion, so I could say, well, if I average out the incoming and the outgoing radiation, it's kind of like a standing wave. So that was the physical intuition about actually getting the average of the two. And that works really well, because if I get the Dilbertian of the singular field, okay, I'll get the box of the retarded function, which is a solution to this, so that'll give me minus 4 pi j. I'll also get the same for the advanced, and these are halved, so I'll literally get back out that the singular solution has the exact same singularity as the wave equation. But what's really nice is that then if I look at my regular, which is the retarded, regular one is the retarded minus the singular, so I'm now taking away this term here from the retarded. So it's the retarded minus half the retarded, which gives us half the retarded, and then minus advanced, and you get minus half advanced. Okay? And that's my regular. And what's nice about that is if I throw that into this, I'm going to go, this is going to give me my minus 4 pi j, and so is this, and now I have a lovely regularized homogeneous wave equation. Okay, so this is seen as the true solution. Okay, and then, okay, you have your field, but from that you get your force, which in electromagnetism, you have your Faraday tensor, and then from that you get your acceleration. Okay, and this was all done by Dirac in 1938. Okay, so very well established. But if you try to do the same thing in curved space-time, you now have curvature terms popping up. So then now you have the, okay, but we still have the same kind of idea of our retarded advance. Okay, now you've picked up a square root of your metric determinant, but still same concept. And then what we have to do is the Hadamard-Green's function. So the idea of these is, let me see if I can put, do I have a picture? Okay. Yes, okay. So the idea with the Hadamard-Green's function, don't get too bothered about it. This thing sigma, think of it as a way of of calculating distance in curved space-time. The main thing is it's 0 on the light cone. So it's 0 here. Okay? So this thing is saying, this is just saying when I'm on the light cone. Okay? I have and this is called the direct. So it's literally this point here that I'm caring about. And then you have a step function. And sigma is also when if your space like it's plus, and if your time like it's negative. Okay? So this is just saying that when I'm time like connected, so in the past, this is going to be my tail term. Okay, so the idea is just being like, the radiation that I can receive at this point is the direct part that just shoots straight to me in a null ray that wasn't bothered by anything else. But I can't ignore the fact that I'm living in curved space-time, so there could have been things emitted in the past that have scattered off curvature and arrived late. And that's these tail terms. Okay, and then you have the same kind of concept for the advanced, that you could have scattering. You emit something that very cleanly arrives, but then you'll have scattered effects that'll arrive later on in the future. And the problem with this is, okay, we all know this off by heart because we went through it earlier. Still on the board, excellent. But one of the nice things about this is when you write it like this, this is actually a way of writing the sigma in flat space time. Okay, it's similar to ds squared. Okay. Okay. Now the problem is, if I try to do what we do in flat space time and take an average of these two, I'm going to have something. So remember, when we took an average of two, we just have to get this point and this point. But now I have something that depends on this point and the entire history, because we don't know how long things have been scattering and how long it takes them to damp, and the entire future of my emitter, which is just nonsense. So it doesn't make sense. So the Detweiler Whiting idea, it's actually not very hard to go through, but we obviously don't have time. But you just add on an extra tensor and kind of solve for it, saying, I don't want this mess. And you put all these restrictions on it, which I won't go into, but basically H ends up being V. And when you put V back in, you end up with a singular field that looks kind of gross to begin with, but then you can just, you end up with this. And what that basically looks like is you end up with a singular field, which now depends on the part of the world tube that's space-like connected to your field point. And that's doable. Okay. Okay, what that looks like when you do it, you could actually see this by eye. So remember I said like, oh, Schwarzschild's circular is the easiest thing. Well, for self-force, it was really hard, I think, for to do the first one. That only came out, I think, in the early 2000s, or late 2000s, like 2009 or something. So actually what they did to begin with is sometimes they would just take a scalar field instead of a massive field. So you have this idea, you do a toy model and you deal with a scalar particle. Then you can go into electromagnetism and then you build up the gravity. And basically the difference is you're just dealing with more indices, which are a bit of a pain. Okay. I mean, if people have time later, you can almost see by eye. This is just when you integrate this over d tau, you do a conversion to d tau to d sigma, and that's why you end up with this underneath, and your U on bottom. And then we just leave this like this. These can be solved. There's basically for everything you see here, there's a known equation. So a lot of time what we do is we write out that tensor in unknown coefficients and powers from how far away it is, throw it into the equation and solve for your unknown coefficients. We won't go into it, but just take my word for it. These can be all solved analytically. That's an example. This is a known thing for this. This sigma guy is the single function. But okay, we're out of time, so I'm just going to, okay. There's several different self-force methods. Okay, I've skipped ahead. Okay, that was all about how to get the singular field. Now the point is you have to go back. Remember, we have to get the retarded field and minus the singular field. So when we talk about solving the self-force, a lot of time people are going, okay, how do I solve the retarded field and subtract this infinity? There's different ways of doing it. One of the first and most successful is you do spherical harmonic decomposition. You can do spheroidal harmonic in the retarded function, and then that goes recast into spherical. But the whole point is you end up with a spherical harmonic decomposition of the retarded and the singular. This is numerical, and this is analytical. And you take them away mode by mode. And from that you can get your self-force. Another way is you kind of, if you think of this situation here, here's your little guy. You kind of encapsulate him in a big world tube. And you say, okay, well, the singularity structure dies. It doesn't exist outside this tube, so I can just solve directly my Albertian equals 0. But inside the tube, I have to be careful, and I have to deal with that singularity. And then the last way is a semi-analytical way where you go, well, actually, I'm just going to, I can actually just integrate the retarded Green's function all the way down. And I have a direct part in the tail. But if I start the integration just below here, I don't have to, I can actually just throw away the singularity, which is a little cheeky, but doable. And this is a semi-analytical way, but it's only been done in Schwarzschild scalar. But basically the idea is you have a local part, which is kind of this part here in a normal neighborhood, and then you integrate over the Green's function in the distance passed. And, yeah, sorry, I just talked about that. The local part, you can do a Heidelberg expansion, don't worry about it. It's just a way of, again, just doing these massive expansions and solving for unknown coefficients. And then to do the distance, it gets a bit tricky. You have to do this whole thing with where you want to integrate from here to here on the real line. You go into imaginary, complex plane, branch cut, sum over quasi-normal modes. Super lazy. I don't do that part. Someone else does it. Anyway, but then at the end, you match everything together, and you have this nice semi-analytical solution, which is cool because it's self-force. All the other ways do it numerically. But it's only done for a Schwarzschild scalar. Okay, so where we are with the current status of self-force. Okay, so I explained to you that it's a perturbation. I got you the equations of motion. I showed you that you have this issue with singularity and how to remove it. And then I showed you the different ways that you can calculate either the retarded field and subtract the singularity, or how you kind of just throw away the singularity at the very start. Okay, so within the self-force, when we say we have things done, sometimes they're done in more than one way. So what's nice to notice here is, okay, so this is, I've stolen this from the white paper again, and it was Josh Matthews who did this. Okay, so this is the package I was talking about earlier, the fast Emery waveforms, 100 milliseconds. It was just released the upgrade was released a few months ago. It is only the adiabatic, but it has Kerr. I don't think actually it has resonance, maybe not resonance. Yeah. Sorry, I should have ended this here. Okay. It goes high spinning, high eccentricity, and you can start really far out. Okay. Now remember when we were comparing the waveforms, the adiabatic isn't really good enough, but for things like doing Mojito simulation data where we don't have this, you can use it, or people can start using it to try to figure out what you're standing. Okay. Okay, the other thing is noting that there's also, with the Black Hole Perturbation Toolkit, they've released the Schwarzschild scalar package. And this I think is in Python, but this is, I think, Mathematica. And this is currently without secondary spin, but the secondary spin waveforms do exist, and you can guess. If you ask Josh or Barry, they'll give them to you. Okay, cool stuff. So I'll go through this really quickly. So some really cool stuff that's happening in self-force. Remember we were saying like it's always for the in-spiral, because they're extreme mass ratio in-spirals, but Adam Pound figured out a way how to do the merger ring down with a load of Belgian people. So basically the idea is you have the 1 PA timescale here. As you go into the transition, it's going to be the post-leading transition, and it scales now as e to the 1 minus 5, or epsilon to 1 minus 5, so you have to get higher on this. And that's a rescaling of your frequency. And then the post-geodesic, so kind of your plunge, is a timescale of epsilon to 0. And this is absolutely beautiful result. So this is comparing to a numerical waveform of Q10. This is the 1 PA in spiral is the yellow. The 2 PLT transition to plunge is in the blue. And the 0 PG is in the green. And the different people who did the different ones. And then that's an NR waveform underneath. So they're starting to get the transition plunge in using the self-force framework too. And that's very, very new. Okay. Also, what's really cool, remember I said like sometimes you have pieces of PN and pieces of self-force. So one idea that came up was like, do we need second order self-force? And basically some people were like, are we just calculating second order self-force to figure out whether we need it or not? So the idea here was someone was like, okay, well once I take the best of the PN, which is the 4.5 PN energy flux, and I only take the first order gravitational self-force energy flux, and I combine these using evolution equations with a flux balance equation, and what happens is it does really well. And so this is like for Kerr spinning, they're aligned, and there's no secondary spin, but again, compared to a Q10 with a high magnitude of spin, you can see it exists really well with the numerical things. That was more about why, don't worry about that, but basically when it's far, it agrees with PN when it needs to be agreed with PN, and it agrees with self-force when it needs to agree with self-force. Okay, so it agrees with 1 PA high mass ratios, but agrees with PN at more comparable masses. So it's actually a way of bridging from self-force into even more comparable masses. But what's really cool is it actually doesn't use the second order self-force. So everyone's like, huh? Anyway. Okay, and then numerical relativity is catching up too. They've done this idea of excising out a big tube around your little particle, and then just outside it using full NR simulations. So the red line is the trajectory of your smaller object. Seeing you excise this world tube out and do a perturbative analytical solution in it, but outside you use your full NR, and that's showing really nice stuff. But it's only in the scalar case, like the semi-analytical stuff I showed earlier. Oh yeah, I was just in a Yeah, this is because I'm doing this stuff now. We have this working in Kerr. Well, that's all I was wanting to say there. And what's cool about that is that we compared it with a different way of doing soft force, and it matches to several digits. Great. Another crazy, scary thing I'll just mention exists is if you have a third body. 3-4 years ago, I'm so sorry, people realized that if you have a system, okay, so if you have like a big black hole, and you have a little black hole, and then you have some thing out here, and it could be in an accretion disk or whatever, you know, this guy can perturb this system. And Beatriz Abanga, Juan Yang, and lots of people have done a lot of work on this, and you get these resonances. And basically what you see here is one is a waveform where they've captured the resonance, and one's where they've missed it much earlier in time. And you see that they start that you get this dephasing. And what's crazy cool about this is everyone been hearing about these quasi-Kemplerian bursts. Oh, everyone's so excited about them in cell phones. You know, what are they called again? Quasi-Kemplerian? Yes, sorry, my brain is dead. These, okay, so these are really, really like one of the new big things. And one of the things everyone was talking about them was that, because their idea is you have this system, and they think like, at the start they were thinking like, okay, maybe you have an accretion disk around here, and there's these flares. And they think it's like maybe a smaller body puncturing through, and that's giving you these flares, and they're matching it all up. And at the start, everyone's like, oh, cool, could this be an emery? We'll have a multi-messenger signature from an emery. And then when they started looking at how far away it is, they're like, oh, it's too far out to be seen by Lisa. But then Beatrice was like, but you know where it's perfect for? It's perfect to perturb my emery. So if you have an emery inside here, and this guy with the exact place where she said they could be 40 years ago, is piercing through that thing, it's also messing up this. So they're actually showing us we have to take care of our environmental effects. Okay, and then, okay, so challenge, good news. First order, it's great, lots of cross-checks. We have these packages that people can play with if you want to do astrophysics, cosmology, whatever, fundamental physics. Challenges, second order is extremely difficult. Do you remember I said you calculate those things off-grid? If you want to do that for generic Kerr, it's going to take 3 billion CPUs. So not great. So that's why we have to keep thinking of better ways of doing things. And things like the environment, like these extra bodies, or the impact of accretion disks, or non-GR, beyond Einstein, these are still being developed, but there is progress in including them into these kind of toolkits. And yeah, then this is just all that new crop that I said. Okay, we're done. Sorry.